Okay, so in this video we're going to start our kinematics unit. This is going to be our first mechanics unit, and basically what kinematics is kinematics is the branch of mechanics. Remember, mechanics is the study of motion, but it's the branch of mechanics that deals with the motion of an object without regard to what caused the motion. Okay, so later this year we'll talk about a unit called dynamics, which basically deals with the why behind motion, what causes the motion. But kinematics only studies motion without regard to what caused the motion. Okay, so basically kinematics is the study of concepts such as displacement, velocity, and acceleration, and how these things change over time. Okay, so finally we get to start the real first unit of physics that we'll see this year. Okay, so let's start with some definitions. As always, as we go through these slides, please make sure that you're taking really good notes. Okay, especially on the next slide, remember that definitions are important. That's a saying I will say throughout the school year and throughout next year because it's true. Okay, so let's start with some basic definitions. Okay, and again, pause here if you need to add this to your notes. Okay, so the first thing we're going to do is define three different quantities. Okay, position, distance, and displacement. Okay, so position you can think of as a single point along a number line. Okay, so if you imagine a number line, with marks, okay, your position that we'll call x is a single point along that line. Okay, when it says with respect to your coordinate system, basically what that means is you need some sense of direction and you need some type of origin for your coordinate system, whereby one direction is positive and the other is negative. Okay, so in this simple example, let's say to the right is positive and to the left is negative. Okay, or you could also have a coordinate system going up and down, where normally up is positive and down is negative. Okay. Now, by the way, I will add there's no reason why that has to be the case. We could easily establish a coordinate system where the left is the positive direction and the right is the negative direction, which might sound a little strange to you because that's not what you're used to seeing in your math classes, but there's nothing that stops us from doing that. Okay, so position is where you are at a single point in time relative to your coordinate system, and we're going to give position the symbol x. Distance, we're going to give the symbol d. When you're talking about distance, you're basically talking about how far you have traveled throughout the problem. Okay, so what is the total amount that you have traveled? Displacement we will see much more often than distance, and displacement is defined to be the difference between your initial position and your final position. Now, when I say difference, I'm talking mathematical difference, so I'm talking subtraction. Okay. Now, the symbol for displacement, at least in the IB world, is a lowercase s. In some other classes, you might see this as delta x, but we use, in this class, we use the symbol s for displacement. And again, by definition, that is the difference between an object's final position and its initial position. Okay, that is how displacement is defined. Okay, definitions are important, so make sure you get this down. Okay, one reason definitions are important is because you can always go back to the definition if you get stuck on a problem. Okay, so keep that in mind. And I said this before, but remember, when you're dealing with physics problems, you need to establish, either implicitly or explicitly some type of coordinate system whereby one direction is taken to be the positive direction and the opposite direction is taken to be the negative direction. Okay, so to kind of introduce the idea of position, distance, and displacement, let's do an example. Okay, and normally I would do this example in person, but I'm going to do this remotely. So here's the example I'm going to do. Here is my classroom, or at least a picture of an animated version of some classroom. Okay, so let's say the left side of the room, let's say that is position x equals 0. Okay, and so I'm establishing my coordinate system. I'm saying that x equals 0 is on the left side of the room, and on the right side of the room, I'm going to say that's x equals 10 meters. Now, there's no reason I had to set my coordinate system like that. I could easily have said, that the left side is x equals 10 meters, for instance, and I could say that the right side is x equals 20 meters. Okay. Now, of course, the room is 10 meters across. There's no getting around that. But I'm free to choose whatever coordinate system I wish. Okay, but for now, for simplicity, let's just say that the left side of the room is at a position of 0 meters and the right side is at a position of 10 meters. Okay, so I'm going to do an example, and I am going to start in the middle of the room right here. Okay, so I'm going to start walking, and I'm going to start at a position of 5 meters. Okay, that's halfway between 0 meters and 10 meters. Okay, so what is my position? That's 5 meters. Now, as soon as I start to walk, I'm going to walk from here to here. Okay, so what is my position now? Okay, well, my position now is 10 meters. Okay, what distance have I traveled? Okay, well, I started at 5 meters. I walked to the right. I'm now at 10 meters. So the distance I've traveled is 5 meters. What is my displacement? Okay, now in this example, I have set my initial position, I'm going to call that xi, to be 5 meters. Okay, and because I've walked to here, at least for right now, my final position is 10 meters. And by definition, displacement is the difference between your final position and your initial position. Okay, so here I would say my displacement is 5 meters. Okay, so far, so good. Notice that distance and displacement can be the same value. Okay, they don't have to be, but in this case, they do happen to be the same value. Okay, so watch what I do now. Okay, so now I'm at 10 meters, x equals 10 meters, and now I'm going to walk back to over here. Okay, what is my position now? Well, my position now, remember at the beginning of this problem, I defined this side of the room to be x equals 0 meters. Alright, so my position currently is 0 meters. What distance have I traveled? Now, I'm not resetting in between here, okay? I started in the middle of the room, and that's still my starting position. Okay, but now my final position has changed. So now my new final position is over here. Okay, so in other words, I went 5 meters to the right, and then I went 10 meters to the left, and so the distance I've traveled is 15 meters. Now, what is my displacement? Okay, so think about this for a second. And remember, you can always go back to the definition of displacement as the difference between your final position and your initial position. Okay, so my final position is 0. My initial position is 5 meters. Sorry, my final position is 0 minus my initial position of 5 meters, and that gives me a displacement of negative 5 meters. You might say, wait, how can you have a negative displacement? Well, the reason my displacement is negative, as we'll talk more about in a minute, is because the negative indicates the direction. Okay, I've walked 5 meters to the left from beginning to end. Okay, now, notice that the difference between distance and displacement is, with displacement, the only thing that matters is my initial position and my final position. The fact that I walked all the way to the right of the room first and then walked all the way to the left does not play into the definition of displacement. In other words, if I had started in the middle of the room, and let's say I went on like an epic journey all the way around here, something like this, and I ended up over here, my displacement would still have been negative 5 meters. Okay, the only thing that matters for displacement by definition is the initial position and the final position. Okay, now ignore that crazy trip I just hypothetically took. And let's do one more example. So I'm now at the left side of the room, and I'm going to walk once more, and I'm going to walk all the way back over to the right side of the room. Okay, what is my position now? Well, now my position is back at 10 meters. Okay, what distance have I traveled? Again, from the beginning, I went 5 meters, and then I went 10 meters back, and then I went another 10 meters back to the right. Okay, so that gives me a total distance of 25 meters. Okay, notice that the distance amount always increases over time because it keeps adding onto itself. Now, what is my displacement? Well, my displacement, I could use the definition of displacement, but if you just think of it logically, my initial position was at 5 meters. My final position was at 10 meters. In other words, I am now 5 meters away from where I started in the positive direction. And so my displacement is going to be a positive 5 meters. Okay, so hopefully that helps you better understand the difference between position, distance, and displacement. We will see distance a little bit, but primarily we'll be working with position and displacement. Okay, so pause there if you need to look at that some more. Okay, so let's do one more quick example involving distance and displacement. Okay, so here is an example. Actually, we'll do a few more examples. Okay, so here we have a skier, and the skier starts at position A, okay, at time t equals 0 minutes, and then they travel from A to B, and then from B to C, and then from C to D. Okay, so the problem says the skier shown above starts moving at position A, and that says that's the origin. In other words, we are, in this case, explicitly setting a coordinate system whereby right here, we're calling that x equals 0 meters. And let's say, just to make things simple, let's say to the right is a positive direction. Okay, now, it doesn't really matter, but let's just go with that for now. Okay, so the question is asking what distance has the skier traveled at position B, C, and D, and what is the displacement of the skier at position B, C, and D. Okay, so I'm going to do this with a chart, or with a table. Okay, so here's distance, here's displacement. I'm going to erase this a little bit right here. And at position A, of course, the distance and displacement are both 0 because the skier has not moved yet. Okay, so what about when the skier gets to position B? Well, when the skier gets to position B, in order to go from A to B, they had to travel 40 meters, plus another 100 meters, plus another 40 meters. So the total distance they've traveled is 180 meters. Now, what about their displacement? Well, remember, their initial position was over here at 0 meters. When they get to B, their final position is at 180 meters. That means their displacement at B is also 180 meters. Okay, so let's take a look at position C. So they go from B backwards to C. Keep in mind that their initial position is at A. Okay, that is fixed. Okay, the initial position doesn't reset when they go to B. Okay, so it's not like you're starting over. The initial position was always at A. So when they go from B to C, in order to get from B to C, they have to go back 40 meters and then back another 100 meters. So the distance they've traveled is going to be their 180 meters, okay, plus the 40 plus 100. And that's going to give 320 meters. Remember, distance is how far the object travels. Now, what about displacement? Okay, so again, you can always go back to the definition of displacement. Okay, here's the new final position, the skier at position C. The initial position is over here at 0 meters. Okay, here, the final position is, again, if you imagine this as a number line, at 40 meters. Okay, in other words, they are 40 meters from where they started in the positive direction. So the displacement here would be 40 meters. Okay, now see if you can finish example 1. What would the distance and the displacement of the object be at position D by the time they get to position D? Okay, so in order to go from C to D, they have to travel forward another 100 meters. That's going to add 100 meters on to their previous distance. Okay, so that would be 420 meters as their distance. And then their displacement at D, okay, that means their position at D would be, let's see, 40 plus 100 from where they started. So their position there would be 140 meters. And so their displacement would be 140 meters at D. Okay, so pause there if you need to take a look at that some more. But you should be starting to get a good grasp of the difference between position, distance, and displacement. Okay, so just to do one more quick problem. Example 1.25 says that a car travels 1,200 meters north before turning around and traveling 1,800 meters south. Assuming the initial position of the car to be at x equals 0 meters, state the final position of the car, the distance traveled by the car, and the displacement of the car. Okay, so let's draw this out. Okay, so it says that the car starts at what they call x equals 0 meters. Now, of course, they start talking about north and south, so now I need to establish some type of coordinate system. And the coordinate system I'm going to use, just because I think most people would agree it makes the most sense, is I'm going to say that north is going to be the positive direction, and south is going to be the negative direction. And again, there's no reason why up has to be positive and down has to be negative. Okay? And again, there's people who will be confused by that, like, how could up be negative? Well, the only reason that you're used to thinking about that is probably because of math class, right? You're used to seeing the normal Cartesian coordinate system where, it's always been like that. That's positive, and that's positive, and that's negative, and that's negative. Okay, but again, that's a completely human construct. The laws of physics don't change based off of, which way we say is the positive direction. Okay, if we throw a ball up into the air, it's going to come back down. Whether up is positive or negative doesn't really change anything. It's a completely human construct. Okay, so just for now, we're going to go with a coordinate system whereby the north is going to be the positive direction and the south is going to be the negative direction. Okay, so the car goes 1,200 meters north. So let's say they go out to here, 1,200 meters. And then they turn around and they go south 1,800 meters. Okay, so this is 1,200 here, and this is not drawn the scale, by the way. I'm bad at drawing. Okay, so they went back 1,200 meters, and then to get to 1,800, that means they had to go back another 600 meters. So that means their final position down here is going to be negative 600 meters. Okay, so their final position is negative 600 meters. And again, how did I get that? Well, just kind of visualizing it. You go up 1,200. If you go backwards 1,800, that gets you to negative 600. Okay, now what was the distance traveled by the car? Well, the distance would be 1,200 plus 1,800, which is 3,000 meters. Okay, so remember, distance is just how far your object has traveled overall. And displacement, by definition, is the final position minus the initial position. Okay, the final position was negative 600. The initial position was 0. Okay, and so the displacement was negative 600 meters. Okay, and so that's the answer to the question. Okay, now the last thing I want to show you in this video, just to prove to you that coordinate system doesn't really matter. Okay, we were told in this problem to assume the initial position of the car to be x equals 0 meters. But let's say we hadn't done that. Okay, so let's just for fun change things up. Okay, so let's say that the initial position of the car is actually, oh, I don't know, 400 meters. How would that have changed the problem? Okay, so the new initial position is 400 meters. And again, I'm just doing this to show you how things change or don't change, okay, if we change the coordinate system. All right, well, if I start at 400 meters and I go forward 1,200 meters, then that gets me to x equals 1,600 meters out here. Then I turn around and I go back 1,800 meters. Okay, so again, if you approach this like we did before, if you're at 1,600 meters, and then you go back 1,800 meters, that would get you all the way back down here to a new final position of negative 200 meters. Okay, so now my final position is negative 200 meters. What is my distance? Well, my distance hasn't changed. Okay, I still went forward 1,200 and back 1,800. That's still a distance of 3,000. What about my displacement? Well, my final position is now negative 200 minus my initial position of 400. And look, that gives me a displacement of negative 600 meters. Okay, and so by changing my coordinate system or shifting, where I started, that didn't really change anything from a physics perspective. Okay, so do keep in mind that in most physics problems, you're free to choose a coordinate system that makes the most sense for you. In most situations, we will use a normal coordinate system, okay, where up is the positive direction and to the right is the positive direction. But if you think there's a coordinate system that works better for that particular problem, then you can decide to use that coordinate system and just write a note under your work saying that this is what you're doing. Okay, so hopefully after this video you have a better understanding of what the difference between position, distance, and displacement are. Please let me know if you have any questions, and as always, I will see you guys in the next video.